So today I'm going to summarize everything that we've learned in chapter 5. So we're going to learn how to choose which test that we're going to use to test the divergence or convergence of a certain series. So it's easy to use the tests once you know which one to use, but it's kind of difficult to determine which one I should start with and see if that would work or not. So that's why we have a problem-solving strategy that we're going to learn today and do a bunch of examples. So the first thing that you have to start with or think about when you have a series, you want to look at it, see, is this series something familiar? Is it something that I already know, like a harmonic series or a P series, a geometric series? These series we know when they converge and when they diverge. So that's why the first step is you look at your series, is it something that looks familiar to me? If that's the case, you can just apply the properties of that series directly. So the first step is you look at it, you think, is it something familiar? If it was like a P series, for example, you want to look at the value of your P. If it was bigger than 1, you know that your series converges. Similarly, for a geometric series, you want to look at the ratio. If the ratio is less than 1, then you know that your series converges, and so on. Now, if that's not the case, you want to look at it. Is this an alternating series? Does it have like -1 to the n or -1 to the n plus 1? Now here, you can just apply the alternating series test directly. And when we're talking about alternating series, sometimes the absolute convergence comes into place, because if you take the absolute value of the alternating series, the negative goes away and it turns into a series by itself where you can test it separately, and then if that converges, then it's absolutely convergent, and so on. So that's a property for alternating series. When you're asked to prove it's like absolute convergent or like conditionally convergent, so it depends on the question. But what if it's not an alternating series? Here I need to think about, is it similar to a P series or a geometric series? It might not look exactly like them, but they look similar to them. So when they look similar to things that we already know, I directly think about comparison tests. We have two types of comparison tests, either the general comparison test or the limit comparison test. So it depends on your question on which test you want to choose. Now, if it doesn't look familiar at all, but you notice that you have either factorials or powers inside of your series. When you have factorials, powers, like we talked in the last video, we can think about the root test or the ratio test. Okay, so which one should I think about first? If you have a power or an exponent in terms of n, then think about the root test first, because you can get rid of that power. But if you don't have that power by itself, then you go straight to ratio tests. So ratio test is very helpful when you have factorials, so keep that in mind. Now, what if you thought about all of these steps, but nothing worked? Here, you can go to the divergence test. The divergence test is pretty easy. You just take your limit. If it's not equal to 0, then your series diverges. If it's equal to 0, you don't know. You want to check a different test. So if it's not equal to 0, then your test cannot provide any information about the convergence or divergence. Then the last step that you go to is the integral test. An integral test is when you take the integral of what's inside of your series as a function, and then calculate the integral as an improper integral, which we already know how to do using limits. If the integral converge, then the series converge. If the integral diverge, then the series diverge, and so on. So that's the steps that you should have in your mind when you want to test the convergence of a series. Now, with practice, these steps would come more naturally. You'll be able to choose the test right away once you look at your series. So I would recommend practicing a lot of examples, either from the homework problems or from the suggested problems, or even the book problems. The more you practice, the more you're comfortable, and it's easier for you to determine which test to use. Now we have these tables. It's just like a summarization of all of the tests that we've talked about. So you can look at them and try your best to memorize all of the conditions and stuff like that to know which one to use. Okay, so let's start with our first example. Now, when I look at this series, I think, oh, this looks like a P series. So since this is a P series, I want to look at the value of my P. Now here, P is 3. Because if you remember, a P series looks like this. So my P is 3. If your P is bigger than 1, then by the P series test, your series converges. That's it. Let's look at the second example. Now, if you look at the second example, I have -1 to the n plus 1. Immediately, this is an alternating series, so I need to use the alternating series test. Now let's look back. An alternating series test, you need to have a decreasing sequence, and this sequence has to converge, has to go to 0, like the limit of your b of n has to be 0. If that's the case, then by alternating series test, your series converges. Now the b of n is anything that's multiplied by the -1 to the n, or n plus 1. So here, my b of n is just 3n plus 1 over n factorial. If you take the limit, now here you can use either L'Hopital's or think about like, oh, the degree of the denominator must be bigger. Here it's bigger than the numerator, so this goes to 0 for sure. Now here, to prove that your series is decreasing, you have to prove this condition. Now if you think about it, 3n plus 1 over n factorial, the denominator is increasing in a faster way than your numerator, which means that the fraction is becoming smaller very, very, very fast. So if you add a 1 to your n, it means it's even getting more smaller in a faster way. So that's why this inequality holds and your sequence decreases. So since these two conditions are met, then by the alternating series test, your series converges. So that's it. So now let's look here. Now if you look here, it doesn't look like something familiar. It's not an alternating series test. It doesn't have factorials. It doesn't have exponents of n. So we need to either think about, can I compare it to something that I already know? If not, then I go directly to the divergence test. Now here, although it kind of looks similar to something like a P series, like in terms of n squared and so on, if you try to compare it with stuff, you're not going to be able to get something that you want. So here, if I make it bigger, I can do this. But the problem is I can't get rid of the 1 plus 4n because I don't know if it's going to be even, it's going to be positive or negative. So I don't know if it's going to make my fraction bigger or smaller if I remove it. So I can't get rid of that, which means I can't do that and get like, oh, this is less than n, 9 over n squared, which converge, and then by the comparison test converge. So this does not work. What could work is like, oh, I can get rid of the 1 and I can get rid of n squared. So this is less than 9 over 4n. Now, although this works and this inequality holds, and this series is a harmonic series which diverges, using the comparison test, it doesn't tell me anything about the series that I want, that I started with. So that's why the comparison test here does not work. So if that does not work, I go directly to the divergence test. I just take a limit for everything that's inside, and then we calculate the limit. Now here you can use L'Hopital's, or like you can divide by the highest exponent. So it's up to you. What I do is like, oh, I look at the highest degree here. It's n squared, so I take that, and then here, what's the highest degree? It's n squared. And then if you simplify, this is just -2. Now -2 is not equal to 0, so by the divergence test, this series diverges directly. Okay, how about number 4? Look at number 4. What do you notice? We have n and n in the exponent. So here I can skip directly to the step where I either use the ratio or the root test. Now, since I have an exponent of degree n, I think about the root test first. Now here, I can rewrite my a of n as 5n minus 1 over 3n plus 1 all to the n. Now, if we want to apply the root test, I take the limit of the nth root of my a of n So now this nth root with the nth power goes away, and I have the limit of 5n minus 1 over 3n plus 1 as n goes to infinity. Then this is just 5 over 3. Now, if you go to the properties of the root test, if the value of the limit is bigger than 1, then the series diverges. Okay, so that's it. You just take the limit and it diverges since it's bigger than 1. Now let's look at number 5. So number 5 here, I have k over 2 to the k. So what test could be helpful here? I can't compare it to something that I already know. Nothing looks similar to it. I can't compare it with stuff. But since I have an exponent, I can think about either the root or the ratio test. Now, we think about the root test first when we have an exponent both in the denominator and the numerator. But here, since I don't have it in the numerator, I go directly to the ratio test. So the ratio test, you take the limit of an plus 1 over an as n goes to infinity. So here I have the limit of k plus 1 over 2k plus 1 multiplied by 2 to the k over k as k goes to infinity. Now, if you simplify, this goes away. I have a 2 here. So I have the limit k plus 1 over 2k as k goes to infinity, and this is just 1/2. Again, since this is less than 1, by the ratio test, this converges directly. That's it. Okay, so now let's look at number 6. Again, doesn't look like something I already know. It's not an alternating series. Although it has an exponent, it's kind of difficult to prove. Like, if you look at it, it has an exponent, not in the new denominator, so I'm going to use the ratio test. But let's see. If you take the ratio test, and simplify, you're going to have n cubed over n plus 1 cubed. Now, if you take the limit, this is going to be equal to e. Now, since e is bigger than 1, then this diverges. Or if you use the divergence test, if you take the limit, I think it's going to be infinity, so it's not equal to 0, so it diverges too. So it depends on whichever you want to use. Okay, now let's look at this final example. I have 3 to the n plus 2 over 5 to the n. If you go through all of the steps, it's going to be very difficult to prove using other tests. But if you look at it, I can compare it with something that I already know. So whenever you have like a number to an n in the numerator and the denominator, always think about the geometric series. So here, I'm going to think about a geometric series that has the ratio 3 over 5. So now, if I take my b of n to be 3 over 5 all to the n, this series here is a geometric series. Now, since it's a geometric series and r is 3 over 5, that's less than 1, then it converges. Okay, now I'm going to use the limit comparison test here. So if that's my b of n, my a of n is the original thing. And then we're going to take the limit of an over bn as n goes to infinity. So now let's plug in the values. So I'm going to do the keep change flip rule, where this is my b of n, this is my a of n, as n goes to infinity. Now if you can see, I can just cross these out. So I have this value here. If you divide by 3 to the n, you're going to get a 1. Okay, now since the limit is equal to 1, which is not 0, the limit comparison test tells me that if it's not 0 and the summation of your b of n converges, then my summation of a of n must converge too. So that's why this series converges. So that's it for chapter 5. It's all about determining whether the series converges or diverges using the different tests and techniques that we've learned. Make sure to be comfortable and familiar with the tests, do some practice examples, and if you have any problems or if you have any questions, just please let me know, email me, and best of luck.